the talk by Olav Rune Godø, our friend from Norway. He is behind most of the equipment that is used by fishermen in Chile, and so he will probably talk to you about technologies that are used lately for fishing and also conservation of fishes.
Thank you, Victor. Thank you for inviting me. Nice to be here. I feel honored to be in such an occasion. I don't speak Spanish and I hardly speak English, but I hope you can figure out something from my slides. I was heavily instructed by Victor to not mention the acronym of the concept marine ecosystem acoustics, because it's a bad word in Spanish, as he said. But maybe you will remember the concept when you figure out what it means. In the wake of the MarEco project, the expedition to the mid-Atlantic ridge, there came up a discussion about this concept, marine ecosystem acoustics. And from there we have developed it, and we have established an international consortium based on partners from Central Marine Life, and it's now becoming crystallized out as an initiative that hopefully will become a strong center in the future. So I'll try to give you some impression or some background for this concept. Firstly, it has a background in our upcoming request about the ecosystem approach in fisheries management. From that perspective, not only the fish stock should be considered, but also all the other components of the ecosystem. And we have to collect data that enable us to understand processes of the ecosystem and as well as modeling. And as far as we can see, acoustics is the only method that enables observation of the ecosystem component with adequate time and space resolution. We'll come back to that. We all know that light and vision penetrates only a few meters from the surface, and sound travel 4 to 5 times faster in the ocean than on land. Godø said that he was talking about silent world, but definitely the ocean is full of sounds, and partly of marine life is created based on the soundscape, which is a strong evolutionary force which form the ecosystem. Even raindrops on the surface creating enough sound to be recorded by sensitive instrumentation at 1,000 meters depth. And also we know that fish communicate with sound. So the fact is that we have a dark ocean where our understanding of what's going on down there is based on mostly indirective observation method, that often the method affects the animals during sampling, and we try to figure out how it's working, but we never know if it's actually correct. But we are not the first one to use acoustics. Whales have developed their own sonar system on an evolutionary timescale, and we are still struggling to become as good as the whale. They use low frequency, long range acoustic for detecting their prey, and they're changing frequency range for inspecting it, and they also use acoustic for catching their prey. And you know, this is exactly the approach used by fishermen. And men and whales have similar demands. They use sounds for communication. I don't know if sound. This is low frequency acoustics, and it could very well be that the first signal was a communication sound. The second signal could be a broadband outburst to get information of some kind of target. One of our colleagues, also corporate partner in the Center of Marine Ecosystem Acoustics, Peter Tyre, he has developed a tag to put on animals where he can record the diving behavior of these animals. Like you see here, 3 types of whales diving to 1,000 meters depth. But at the same time, you also can record the sound production of the whales. And I was very fascinated by this picture he came up with, because this is an echogram, like the echogram produced by fishermen or by scientists towards what's going on under the sea. And you see time here and you see distance here. This is relatively close to the target, but this is an echogram showing that whales are using frequencies about 40 kilohertz to detect their prey and approach their prey here. And when they come very close to the prey, they switch to a high frequency broadband signal that enable them to navigate on millimeter scale to catch their prey. This is far beyond what we are able to do today. So we have a lot to learn from the whales. But when it comes to understanding of ecosystem, this is essential. How can we understand, how can we model ecosystem without being able to observe on different time and space scales? With acoustics, we can observe at millimeter scale, at centimeter scale, at meter scale, and also at ecosystem scales by exploiting the bandwidth from low frequency to very high frequencies. If you look at technologies observing the ocean, we can use satellite technologies with wavelength in the light spectrum and the microwave spectrum, but they will only see what's on the surface. Using laser technology, we can penetrate to about 50 meters or 40 meters and see what is in the very surface. With acoustics, we can penetrate to the deepest part of the ocean. So it is possible to get a full picture of the whole ocean. So the ecosystem concept is building on the challenge of observing the ecosystem at the right time and space scale. And we want to use bandwidth, that means high and low frequencies, and beam width, increasing the observation volume of our acoustic systems. But also, sometimes we have to approach the animals and the process where they occur in the ocean by putting out some kind of instrumentation that is close to the process, and thereby we can increase the resolution in time and space to be able to get the appropriate information. Now some examples of what we have available. This is the new echo sounder, wideband multi-frequency echo sounder. 500 beams, and you can get a whole school in one ping. And what you see here is something that was impossible to observe before. It is a school of sand eel, and sand eel is a species that is hiding in the bottom sediment during night, and also when they are attacked by some kind of predator. So the fascinating thing here was that actually while most of the fish were up in the water column feeding, they always had a foot on the bottom. Some part of the animals were actually from the bottom and up to the schools. And we were wondering, why did they do this? And it's quite clear. They need a very special habitat to be able to escape if they are attacked. So these animals in the foot, they are there to make it possible for all the animals to go through the foot and down into the ground to hide in the gravel. In this way, by observing in the right time and space scale, it is possible to understand processes in a completely different way from before. The same time of system we are using sideways, 500 beams, and including a whole school in one ping. And here you can see a school of sprat. Every ping is telling something about the school, and it gives us information of the detailed dynamic of schools that we never had before. One of our students have been looking in detail of these data. These are school data of herring over 5 seconds. Ping 1, 2, 3, 4. The school is included, the whole school is included all the time, but you can see that the backscattering or the strength of the signal is changing a lot from the first to the last ping. And this is because part of the school, having a horizontal aspect to the sonar in the beginning, suddenly they change aspect, and you get a tail or a head aspect with backscattering, which is only a fraction of the original one. So we can deduce the behavior of individuals within the school with having this modern technology. I was talking about expanding bandwidth. We are normally now operating with instrument keel with 6 frequencies. Each frequency is making an echogram, and each pixel on each echogram can be compared, giving us a frequency response of the recordings. Sometimes the frequency response can be falling, it can be flat or increasing. This spectrum over the frequency characterized the recordings we have had. And we get the picture like this, with the original recordings, and a characterized recording on this side, showing that there are different categories of animals in this water column. This is relatively complex, but it can also be made simple. Fishermen like this one very much, because here they have recordings of herring and mackerel. And you know, in Norwegian water, it costs a fisherman, if it takes mackerel in the wrong section, it costs almost $2 per kilo. So instruments can be refunded in only one catch, if they can avoid doing that mistake. Going to low frequency is a challenge. Normally, in fisheries, we are operating from about 20 kilohertz to 200 kilohertz. Going further down creates a problem with respect to the size of the transducers. We are exploring now the possibility of going to down to 500 hertz by using a technique normally applied for bottom mapping. By going this low, we can get resonance in the swim bladder. If you have resonance in the swim bladder, we can estimate the size of the fish. What you see here is resolution on centimeter scale of the behavior of krill at deep water. What you see here is what Nick McCrease is going to tell you about later. It's resolution on population scale, 50 kilometers. So simultaneously using this technique, you can see what individuals are doing and you can see what population are doing. That's crucial to be able to model fish populations. I think I will, vehicles that can explore the ocean autonomously will in the future be very important. This is just a simple example of a vehicle with communication, telephone communication to the vessel, and a mission plan going to a certain depth, observing the distribution of marine life and the density of marine life, and giving the information to the vessel. This is a layer of herring. You can't see what individuals are doing in here. But if you lower instrumentation to the layer, you suddenly get the resolution on individual level, and you can actually estimate the swimming speed, direction of the individual fish within this layer. Not only that, but one of my colleagues looking at the pulsation of the signal from these individuals. So this is one individual herring swimming with a pulsing signal. And he found out this pulsing signal was actually the tail beat of individual fish. So that is the degree of detail you can find by using the right acoustic system. Putting sensors on location is, as I said, important. And what is happening nowadays is that everything gets smaller and easier to operate. You can put it into different vehicles. And I'm not going to talk about these systems which we have developed, but definitely they become more and more important in understanding the ecosystem. Mid-Atlantic ridge, we could observe by a physical interaction directly. This is internal wave, and we even saw internal wave breaking over the seamount, creating availability of new food to the animals. This is a whale diving from surface to mesopelagic layer for feeding. When we analyze the signal, it shows up it's not one whale, it's two whales swimming very close to each other. Seasonal variation. It's the same buoy at the Mid-Atlantic ridge, and here in September, it is passed by the subpolar front. So it entered from one ecosystem to another ecosystem during one day or 1 week. By having an instrumentation there, you can have a correct timing of processes. By using this kind of instrumentation, you get a picture, but it's only from location, and it's not the full picture. It's the picture of with the right time scale without the geographical scale. And this is mesoscale addies observed from satellite. This is a mesoscale addy observed in the Norwegian Sea by acoustics. And here you can see that mesoscale addies, 60 kilometers, they structure the ecosystem from 1,000 meters to the surface. This is a gadoid swimming at surface, which normally is at 500 meters depth. So these physical processes is creating the ecosystem also at higher trophic level. We always have to sample, but sometimes I'm wondering, what do we get out of trawl sampling? Going through a system like Mid-Atlantic Ridge, where dynamics is taking place all over the time of day. There is a lot of selection, there is a question of distribution, and there's a question of avoidance. We never get the right picture by sampling with trawls. There's a question of availability of ships. Chile has a lot of high-quality fishing vessels. This is a Norwegian vessel equipped with a protruded keel with acoustic instrumentation. It can be loaded on land and put into the vessel. Suddenly you have a research vessel. Acoustics observing methane seeps on bottom. That is a much more important impact factor on climate change than CO2. It can be observed with acoustics. Finally, we think that we can see the sea with sound, and operating with the appropriate vessel-based and stationary system, it is possible to get the complete picture, at least a picture that's much more complete than it used to be. Thank you.
Thank you for this superb talk. Maybe we can just have one question. We are late for our coffee break, but one question here on the left on the aisle with the microphone.
Hi, I'm Andrea, a marine ecologist. I think this is very important because I've been reading a lot about ocean noise and how it disturbs the dolphins and stuff. So I have kind of two questions. Since you're studying mackerel and herring, which are very important prey for large whales and some dolphins as well, have you been in a place where whales and dolphins are trying to catch the school of fish and you are already using this disposal? And since the strong noise and maybe strong sonars can damage the middle ear in dolphins, and it takes them about half an hour to recover, from this crazy noise. Do you think this causes more damage in dolphin populations and maybe causing mass strandings?
I'm not quite sure I got your question correct, but are you asking about the impact of sound?
The impact, and if you can use this sonar to study movements of dolphins and whales while they are catching the fishes.
Yes, there is a lot of question about this, and we have a project going on actually now using to study impact of military sonars, which are the strongest sonars, and at the low frequency that impact a lot of marine mammals or marine animals. It's so surprising to see. Herring is a hearing specialist, and military sonar is going right into their hearing frequency. But they are ignoring the military sonar. If we replay signal from a killer whale, which operate in exactly the same frequency range, they're flying. So they can understand what is a mechanical signal and what is a signal of threat. So I think we underestimate these animals in how they can interpret sound. Of course, military sonar with its high performance is very close to some fish and to marine mammals. It will impact their hearing ability. We have seen some indication that diving frequency of some ways change when there are military sonar affecting them in the neighborhood. But I think when we look at the sound level you see here and the possibility of the animals to fly away from the source, I don't see a major threat from military sonars, and when it comes to the sonars we normally are using, they are way beyond the hearing range of most marine animals and will not affect them at all.
Thank you. Now we will